All right, guys, we're just going to go ahead and walk us through my response to the gallery walk number 2 here, as I promised. So I've already made notes in it, so I'm just going to highlight some of those notes. And let me know if you have any questions. All right, well, let's start with the prompt A, which was Team 7. This one is all about the control of stroke volume. Okay, so preload, afterload, and contractility. Preload, afterload, contractility. Okay. Everything this team has here for preload is good. I wanted to highlight the 3 factors that are the kind of the mechanisms for why preload increases stroke volume. We've got the stretch of the heart, which leads to increased bounce back. That's number 1. Number 2, by stretching out the heart, the affinity for calcium on troponin increases. So more calcium binding to troponin means more actin-myosin interaction and stronger contraction. And then lastly, if we stretch it out a little bit, it puts us in a better position for the length tension relationship. And what I would recommend for these, for increased muscle pump, increased thoracic pump, increased pulse wave, is to just explain it a little bit, right? Just say something simple like, because we're contracting more muscle, we're smashing down veins more and we're pumping more blood back. Because we're breathing more, we're smashing down veins more and we're pumping more blood back. That's the thoracic pump, right? Because our heart is contracting more rapidly and faster, our arteries are pumping against veins more and the pulse wave is happening more. And the vasoconstriction of veins, you guys did explain that one. Okay, for afterload, you explained it nicely. The one thing you didn't really completely close the loop on was this thing I wrote in here at the bottom. So yes, everything you said is true, but what does afterload actually do during exercise? It goes up, right? Because blood pressure goes up. And then what does that specifically mean for stroke volume? Well, it makes it harder to open up the aortic valve during exercise, right? And so then that fights against the increase in stroke volume that we need to see. So this one is kind of fighting against us during exercise a little bit. Okay, and then last, contractility. You had it all there. The one thing I would just make sure you mention is that this is controlled by the sympathetic nervous system, right? As we increase activity on those cardiac accelerator nerves, we increase calcium in the heart muscle cells, and then we increase actin-myosin binding, and that's how we get more force. All right, that's A. Now for B, this one was the one on metabolites, okay? Couple things that I wanted to add here. Number 1, for fatigue, heat is a part of this, muscle temperature, make sure you connect that. Okay, this one here on how do these metabolites allow us to increase exercise intensity? Well, in order to exercise harder, we have to breathe more, right? We've got to increase ventilation, we've got to get more blood to the muscle, increase vasodilation, and we got to drop off more oxygen, right? So that's the rightward shift. So all of those things that are happening because of CO2 and temperature and hydrogen, those are all necessary for us to exercise harder, right? So then how is this connected to increased AVO2 difference? Well, yes, vasodilation and getting more blood in the capillaries, that's part of it. But then also the rightward shift of the curve, right? If we have a rightward shift of the curve, we're going to drop off more oxygen and increase our AVO2 difference. Okay, and then how do they stop us from exercising? Well, I point back to the fatigue section up here, which is important. And one way to think about this is kind of like a Goldilocks type idea where we have the metabolites kind of coming up, which is pushing us harder, activating our metabolism, getting more vasodilation, making us breathe more. It's going up, up, up. And then at some point that kind of levels out, the effect of that, and then it starts going down, right? We get too much hydrogen, too much CO2, instead of that pushing us to go exercise harder as it was here. Now it's starting to not allow us to exercise and starting to go down. So there's kind of this sweet spot of maximal stress, right? So maximal stress, which leads to our maximal exercise. But once we get past that level of stress, we can't push ourselves anymore and it causes us to fatigue. So it goes from positive feedback on this side over here now to negative feedback. Okay, so that's pretty much it for that one. So team 5 with C here. You have some of them here. I just felt like it was a good idea to go ahead and give you a nice solid outline of what I want you to know. There's 4 factors that increase AVO2 difference here. Okay, and you had some of them there, but I wanted to outline it. So number 1, vasodilation. Okay, and don't just say vasodilation, but tell us what causes the vasodilation, right? Increased CO2, decreased oxygen, increased hydrogen, increased temperature. Those are all vasodilators, okay? Those lead to more blood in capillaries, so then we drop off more oxygen, okay? Number 2, we increase blood pressure when we start exercising. This squeezes plasma out. This causes hemoconcentration. You guys had hemoconcentration here. Just need to explain the part about the blood pressure squeezing the plasma out. Number 3, the rightward shift of the curve that we've been talking about. This is due to CO2 increase, temperature increase, pH decrease. That leads to more oxygen coming off of the red blood cell, which would lead to a larger AVO2 difference. And then lastly, we increase mitochondrial activity, right? And you guys said this down lower, but this would decrease the amount of oxygen in the mitochondria, which would increase the diffusion gradient, which would mean more oxygen moving in that direction. This one here, you guys said oxygen extraction by increasing hemoglobin concentration. They said this causes the rightward shift. That doesn't cause the rightward shift. The rightward shift is caused by these factors that I have up here, number 3. Okay, rest of that is good. Okay, team number 4 with the equations. Just wanted to note this is all good and correct. This would be the highest VO2 max ever recorded in history, but just so you know, but it's still fine to do the calculation that way. 100 mLs per kg, we've never seen that quite so high, but it's a fun one to work with. Make sure you know that this comes from that table, right? The RER to kcal table. Okay, these calculations were correct. The buffering system, you got the equation right here. I wanted to kind of clarify with both the RER one and the ventilatory threshold. With RER, you talked about how it gets above 1.0. I wanted you also to say how it got to 1.0, right? So RER gets to 1.0 first by shifting away from fat burning to carb burning, right? And that's what we do there. So it's getting us up to 1 to be total carb burning, 100% carb burning, and then it gets up above by the buffering system. Okay, same thing with ventilation, right? We see ventilation increasing here as our CO2 production increases, right? Because every time we use more oxygen, we also produce more CO2 by the metabolic waste product, right? It's going up, more CO2, it's increasing. But then as we get to this point, right around the same point the lactate threshold occurs, now it gets steeper, right? We're still producing more CO2 because of the more oxygen usage, but we're not staying on the same path anymore. We went up here because of the extra CO2, right? The extra CO2 from the buffering system. So that's important. Important in both of those to talk about what happened before the threshold or what happened before RER got to 1.0. Why did it keep going? Okay. All right. Then this thing with the Fick equation was you guys did great here. Yeah, heart rate, stroke volume, we got all that. Nothing really to add there to that. Very good. Okay, team 3 with prompt E. We have the VO2 stuff. All of that is good. Your definitions are good there. Your lactate threshold definition is good. Just make sure you note that both these definitions are needed. The point at which lactate accumulates in the blood, okay? But then what's actually causing that? Well, it's when lactate production exceeds lactate clearance, okay? We're making more than we can deal with, so it starts showing up in the blood, okay? A couple of clarifications. What does heterogeneous mean here? Heterogeneous means that there's a large spread of VO2 max levels. Some are really high, some low, some in the middle, right? If we've got that good spread, then we'll see VO2 max being a good predictor of endurance performance, okay? But if it's homogeneous, like you talked about down here, all with similar VO2 maxes, then VO2 max doesn't tell us much about endurance performance. Then we need to use lactate threshold because lactate threshold's going to get us closer to predicting a VO2 that's sustainable, not a VO2 max. A lot of times students get that confused. What VO2 is their sustainable VO2? What's the highest oxygen consumption they can keep up and run at that? That's not their VO2 max. It's a sustainable VO2. Okay. All right. So yeah, and you said lactate threshold is a good predictor of maximal sustainable energy or percentage of VO2 max is sustainable. Perfect. Just wanted to remind you all of this. This would be intensity over here. Okay. So intensity, here's lactate threshold, right? Here's VO2 max. And the intensity we can sustain is somewhere in the middle of those two, okay? So it's definitely above lactate threshold, but it's definitely below VO2 max. Okay, so what we're looking for in those people that all have the similar VO2 max on those elite athletes is we're looking for where does this maximal sustainable intensity occur? Does it occur at like 90% of VO2 max? Is it more down here at like 70%, right? Because the one at 90% is going to be the faster or better endurance athlete. And this example here is perfect of the two runners from the notes. Subject 2 probably has a higher maximal sustainable intensity, right? And that's the key there. Okay, number 2, or team 2, prompt F on the atherosclerosis. This is fantastic, you guys. Fantastic. I really couldn't add anything to that. You guys did a great job there. Nothing for me to add. You got it all. Team number 1, prompt G on the effects of exercise on type 2 diabetes. Couple things important to think about here. Definitely the acute and chronic responses for insulin resistance are driven by both AMP kinase, this one, and the calmodulin pathways, right? So the AMP kinase and calmodulin. One thing just to know and make sure you understand is that AMP kinase gets activated when this ratio of AMP to ATP goes up. AMP is what happens when we break down ATP to ADP, right? And then ADP even further to AMP, that's 1-phosphate. Okay, so that happens. We increase that ratio when we do a lot of metabolism, right? So exercise breaks down ATP, it breaks down ADP, and it increases this AMP to ATP ratio. So I want you to connect it directly to exercise, right? And then the calmodulin pathway is activated when calcium levels are high in the cell, right? We know that exercise causes a release of calcium inside the cell, so that directly activates calmodulin. Okay, PGC1 alpha is key here for sure. There's really 3 chronic effects, and you guys have them all here. I wanted to just reiterate them here. Okay, I want to reiterate those chronic effects. And then also the thing that you did kind of leave out was how do these chronic effects lead to lower glucose, right? That's the bottom line. Problem with type 2 diabetes is glucose is high. That's one of the problems, right? So how do these effects actually decrease glucose? Well, number 1, chronic effect is more GLUT4, right? GLUT4 is the gate for glucose to get into muscle. So if we got more GLUT4, we get more glucose uptake. And then number 2 and 3 are related. We get more mitochondria in muscle. And then we have some fiber switching from type 1 to type 2A, or sorry, from type 2A to type 1, or from type 2X to type 2A. So the fibers become more oxidative. And then the bottom line there is more oxidative fibers use more glucose than anaerobic fibers do. So that's going to help us lower our glucose levels. Okay, let's talk about the liver. The liver next. One thing I wanted to make sure we all understand is that when the liver has insulin binding to it, that should be communicating to the liver, stop releasing glucose. We don't need you because we've got enough glucose here. Okay, but during type 2 diabetes, the liver is less responsive to insulin. Okay, and that's connected to the fat buildup in the liver, which is connected to visceral fat. So increased visceral fat usually means increased liver fat, okay, which means liver insulin resistance, which is this idea of being less responsive to insulin. So exercise has shown the ability to decrease visceral fat, decrease liver fat, and make the liver more responsive to insulin, so it stops releasing glucose when it's not supposed to. And then lastly, with the pancreas, you guys talked about the pancreas here and kind of what it does, but you never really said exactly the effects the insulin can, or that exercise can have on the pancreas. So those are two I wrote down here, which are very important for you to know. Number one, exercise can increase production of insulin and storage of insulin in those beta cells. This is mostly seen in animal studies, but we've seen some hints of this in human studies. And then number two, we see that exercise can directly increase the amount of insulin released by the pancreas. All right, guys, that's it. Study hard and good luck on Wednesday.